Okay, so we are back at Haskell and higher order functions. And that is just that functions return functions, so they become higher order. Layers of abstraction, I don't know. So curried functions is what we learned yesterday was that if we call this, we're actually calling a function that calls a function. Right, we return a function, and this is the function, max 4, and it only takes one parameter, because in Haskell, all functions only take one parameter. Right, and they can take functions as parameters as well. There we go. So this makes sense, right? This is why we have this structure. Because we have the parameter and we have what it returns. And this is the parameter and it returns this function, or a function that looks like this. Yeah, that's why we put the parentheses here, to just show that that is actually what is happening. Same here, we start here and we return functions that do this. Okay. That all made sense. The curried functions. Well, conceptually it makes sense that this is the way it's done. And here we just conceptualize it some more that show that, well, this returns this function and this returns this function. Just showcasing with parentheses. That's pretty good. Right, and then we started talking about what was it? What was the name of it? Right, you don't call the full function, right? Because we have the mult3, and then you can create another sub-function. What was that called? Oh, that is curried functions. Oh, right, we're creating our own curried functions. No, I was thinking about when we just take half a function, so to speak. Creating these new functions, didn't they have another name? Right. Let mult2 with 9. Exactly, we multiply those with that one. Is that a curried function? I thought that just curried functions was just this. This is a curried function. But no, you create a curried function is when you create your in-between function, I guess. More Persona 5, nice. Right, by calling functions with too few parameters. Yeah, exactly. That is what we talked about. Yeah, so to speak, we are creating new functions on the fly. What if we wanted to create a function that takes a number and compares it to 100? We do something like this. Right, this is where I got confused, where we removed the x for some reason. That confused me. Partial application. Yes, exactly, call getIn untapped. Yeah. Mult3 9. This is a partial application of mult3, right? Because, right, this is the structure of mult3. So we create a new function that is just... But we don't have the full structure. If we just call mult3 and 9, we throw an error, right? We need to add two more things for this. Yeah, we need to finish the entire application of the function. And we do that like this. By adding the next two parameters to end up with this complete structure. Yeah, this is a partial application because it's not done. needs 2 parameters. All right, compare with 100. We just take something and we get an ordering, yeah. And that thing is a num or ordered thing, or ord type class. And we compare 100 to x. No. Compare with 100x is equal to... Yeah, we return this function. If we call it with 99, it will return a greater than. Yep, simple stuff. Notice that the x on the right-hand side on... Wait, x on the right-hand side on both sides of the equation. Yeah, we have an x here and an x here. Now, let's think about what compare 100 returns. It returns a function that takes a number and compares it with 100. Wow, isn't that the function we wanted? We can rewrite this as... Alright, that's something I want to check. So if we go over here, and we... GHCI, it is, right? And we check the type of what? Compare. Yeah, it takes something and then something else and returns an ordering. Your head is in the way. Oh, sorry about that. Let's just do that. I was just looking for compare, the structure of compare. Coleman122 says, gotta love how randomly I just hear this code jumble, and sometimes I feel like, what are they talking about? You're not alone, Coleman, yeah. I'm actually reading this stuff and the one talking about it, and I have no idea what I'm talking about sometimes. Haskell is hard, man. Alright. So compare 100. Right. That is our... Yeah, if we take, if we type it out... Oops. Ordering, right? This thing. Oops. Sorry. What we get when we call compare 100 is that we have already taken the first, right? So we get this. Oh, sorry. Why are there 2 arrows there? Don't need that. So we only need... Exactly, we only need this number, right? Notice, yeah, now let's think about what compare 100 returns. It returns a function that takes a number and compares it with 100. Yeah, wow, isn't that the function we wanted? Now we can rewrite it as... Yeah, that is the problem I have. Why don't we explicitly state this? It's super confusing. I know that we state it over here, right? That we need something. But how does Haskell know that it's supposed to be here? This rewrite makes no sense to me. Because this is not declarative. Like, at all. Here we declare that we do, this is the one we're comparing with, but here we don't have to. It bothers me. Banana Wolf Monkey says, same, I don't even program, lol. Nice. Just good things to fall asleep to, I guess. Alright, we can do this. This Colgate in on tap that we do IT compare 100. Yeah, exactly. That's what I was thinking. This is what we get. Right, we get the num here as well because the 100. Yeah, that's what compare 100 does. Yeah, I know that compare 100 compares a number to 100, but I feel like this syntax, the way of writing this, is just needlessly confusing. Why wouldn't you just specify, declare? Oh, my head is probably in the way. Like down here, we specify. This is what we compare 100 to. In here, we don't specify. In here, we just say compare 100. I really dislike the syntax because compare 100 with what? It's awful. That's all we need. X is bloat. I disagree. X is bloat. I get it. I get that X becomes bloat because we declare it right here. Since we declare it right here, X is bloat here. But I'm talking about readability. The readability of this is awful. Compare 100 takes one argument. There is no need to specify it. Readability. I disagree. There is a big need. Right. As you said. Boom. Well, it's awful because you're not used to it. Right. Let's say it doesn't matter if I'm not used to it. Say, can I clear this screen? All right. Let's say, oops, that I just create a definition that I say compare 100 equals to, no, shit. What name did they call it? Compare with 100. All right. Compare with hundo. Right, actually, yeah, we don't even need that. Compare with hundo. And then we just do compare 100. And if we just find this out in the wild, right? If we're reading someone's text and just find this, it's not beginner friendly. The syntax is awful. Because, right, I need to know exactly what compare does, which puts me, the reader of the code, in an awkward position. And if we create our own functions, which we will, right? That's the whole plan with the higher order functions, is that we implement and create our own functions. This is just a built-in thing, right? If I do my own function and we just find this out in the wild, this means nothing. This puts me in a position where this is not readable. I have to do extra work to understand what this code does. In here, it's fine because we can get it from this line. But it kind of assumes that everybody who writes Haskell will write this line, which I again forget what it's called. The type class line, right? Because I could understand from here. Yeah, when I learn Haskell and get used to this, I could get it from here. But if we don't get this line, and we don't do it with a built-in function, but with our own function that we defined elsewhere, right? If we define compare somewhere else in the code, I cannot decode this as a user. When you're more comfortable with Haskell way, it is quite readable. You can type out X's if it makes it more readable for you. Yeah, I think I'm definitely doing that. When we're in a simple level here, but If we increase in complexity, then yeah, oof. But I think I understand it now, right? Why you can remove it, because it's there, right? The number that we take, it's here. It has to take another number, therefore, well, it has to take one of a member of these type classes, and therefore Haskell, the compiler, can just infer. Yeah, we got the static, just inferring again. Well, GitInnoTab says that's also kind of like in mathematics. Take x out from both sides and it stays equal. Yeah, I was thinking about that. But yeah, it stays equal, but since the user or whoever is calling this need to supply x, right? If you take both x's away, then the user don't get any indication that they need to supply x. Yeah. Right, the type declaration stays the same because compare 100 returns a function. Compare has a type of, yeah, we checked this. Ord a, and that returns a function that returns an ordering, yep. And calling it with 100 returns something that's part of num and ord type class. The additional class constraint sneaks up there because 100 is also part of the num type class. And that makes sense to me why the num jumps in here. Right. Yo, make sure you really understand how curried functions and partial application works, because they're really important. I mean, really is a strong word, but I think I understand kinda how it works. So let's move on. Hopefully. We might have to come back to this. Worst case scenario. Infix functions can also be partially applied by using sections. To section an infix function, simply surround it with parentheses and only supply a parameter on one side. That creates a function that takes one parameter and then applies it to the side that's missing an operand. An insultingly trivial function. Alright, divide by 10. We have a floating type class. We got one of them and we return another, indeed. Oh, divide by 10. Right. That lets us, by doing the parentheses, lets us make it into a prefix function. I thought we can both do it this way, divide by 10 and what? 190. But we can also do it this way, right? Oh, sorry, wait, that was the wrong way. Yeah. But that's because curried functions, right? Yeah. Because this is a function. This is another function. This one takes... Yeah. Curried functions. Well, GitInnoTab says, it's pretty rude to insult with such a trivial function. Not at all. Please, give me trivial functions. Calling, say, divide by 10 to 100 is equivalent to doing 200 divided by 10. As is doing... yeah, exactly, that's what we tried. Divide by 10 or 200. A function that checks if a character is supplied to it is an uppercase letter. Wait. Function that checks if a character is supplied to it is an uppercase letter. Oh, I was confused, yeah. This is a function that checks if it's an uppercase letter. True, false. Yeah. Right, and here again, I would prefer if it said, is upper alphanum X, let's call it X. And then X LM A to Z. I find it definitely more readable, but I get it now. That we can know that since we know that LM takes two variables, two parameters, we know that we have to supply the parameter, since we know what LM does. If we don't, then we're fucked. Right. The only special thing about sections is using hash. From the definition of sections, wait. We were talking about... Oh, section is the parentheses. Right, yeah. In divide by 10, you didn't even notice the missing parameters. In here? Oh. I mean... Like I said, right? Insultingly trivial. Learned division in math like so long ago, so I won't notice it. LM I learned, what, a couple of days ago, so it becomes more noticeable. And compare, I didn't learn that. So it all depends on this function, how readable it is. So I would say that the insult here is, right, assuming that the reader knows exactly what every function does, especially if it's a function we created ourselves. Right, there's a cat in the way here. There we go. Well, he's not running away. Usually he's just immediately running away when I pick him up like this. Right, the only special thing about using is using that minus, the minus function. From the definition of sections, -4 would result in a function that takes a number and subtracts 4 from it. However, for convenience, this means -4. Yeah, exactly. A -4. I mean, not -4, but -4. It doesn't mean subtract, it's just a negative number. So if you want to make a function that subtracts 4 from the number it gets as a parameter, partially apply the subtract function like so. Oh, we type it out, subtract. Yeah. That makes sense to me. Because we want to be able to deal with negative numbers, right? Or minus numbers. Yeah, and that makes sense. What happens if we try to just do mulp334 in GHCI instead of binding it to a name with a let or passing it to another function? Alright, that's our function. No instance for arising from the use of print at interactive. Possible fix, add an instance, declaration for show, wait. This is all right, so this error message is all about GHCI, right? Because of how EHCI does work. So it's a specific error message for this rather than, right? The error message, if we did this within a function, it would be different because Haskell is not an interpreted language. This is specifically for GHCI. Right, yeah, print it. That's the problem. In a do expression, print it. But we can kind of, right, add an instance. Yeah, the error message isn't really straightforward. Functions are not members of show type class by default. Yeah, exactly. That's why I was saying that show is kind of... The problem arises from GHCI calling show in the background, right? Trying to print stuff in the background. So the error message becomes confusing because the error message doesn't reflect the problem with these functions. The error message, right? EHCI is telling us that the expression produced a function of type A to A. Why does it say T when our friendly author says A all the time? I've been curious about that. Why does the GHCI start using T? It's used that a couple of times. Is there any specific reason for it? No idea. Is it just that it might be text? Right, like we would use X for numbers? I don't know. Maybe not. There probably is some reason. Yeah. Probably. It's a little bit confusing, but it's equivalent, right? There's probably a reason, but that reason doesn't matter to us. Right. But it doesn't know how to print it to the screen exactly. Oh. So we can imply, okay, I get it. It doesn't know how to print it to the screen because the function is broken somehow. Yeah. Functions aren't instances of the show type class, so we can't get a neat string representation of a function. When we do, say, 1 + 1 at the GHCI prompt, it first calculates that to 2, and then it calls show on 2 to get a textual representation of that number. And the textual representation of 2 is just a string 2, which then gets printed to our screen. Oh, right. And this does not return something that has a textual representation. And that's why that's the T. They say T here for textual representation. And it doesn't really matter, but it must be what they think, right? Like you say, functions they are not members of the show type class. And that's why GHCI breaks, because what do we return? We return a function. And a function is not printed. No, a function is called. Okay, yeah. So in GHCI, when we get an error like this, no instance or show, it's because we have not gotten something that we can print, which we can infer that we're probably working with a function right now. That at this location, we return a function that cannot be printed. Yeah. GHCI says that the probable fix is making them an instance of show. Yeah, that's... I don't know if that's the best solution, but yeah. I suppose we could make it into a solution. Banana Waffle Monkey says, what's a compiler? Oh, nice. Okay, so... languages work... programming languages work in two different ways, I think. Right. We write our code in a language, Haskell or C or like any of the other compiler languages. Then we have our file with all our text. We then compile all our programming, all our code into machine code, right? Because the machine is just switches of ones and zeros, right? Our machine does not know any programming language. Our computers are just a bunch of switches that do things. So our compiler takes human written code and translates it into machine code that the machine can run, right? It creates a binary file. It creates an executable file. That would be the Windows lingo, right? It creates an .exe file. And the .exe file doesn't look like a... Yeah, you don't read the code in a .exe file. So the compiler is just that. It is what makes the language a language. The Haskell compiler takes all Haskell code and translates it. And then we have languages like Python, which is an... what's that word? Interactive? No. It runs... it translates in real time, so it never... It runs the actual Python file. When you call Python on a file, it just goes through your file and run it immediately. Interpreter, there we go. Instead of a compiler, you have a Python interpreter. So you don't have to create another executable file because the executable file is Python. That is the executable file. I don't know if that was a good explanation between the difference. You can just see it as a translator. Makes enough sense to me. Nice. Enough sense. That's good enough. Where were we? All right. When we say, yeah, some higher orderism is in order. Oh no. Higher orderism? Right. Functions can take functions as parameters and also return functions. That is what you keep telling me, yeah. To illustrate this, we're going to make a function that takes a function and then applies it twice to something. Apply twice. Right? So we take... Right, now I kind of feel like, why is this parentheses here? Right. Function on x, and then we take the function and apply it on the function of x. Right. This is just an order of operations thing, right? And first we take... Let's say that we take... Oh yeah, it doesn't matter. A function that works on numbers. Like, we can say that the function is add 3. So we put in the number here, we add 5, and then we add 3, so we get the function. But since we have the parentheses, we get 8 here. No, I'm confused with the parentheses. Alright, first of all, notice the type declaration. I need to learn that. It's called the type declaration. Before we didn't need parentheses because the arrow is naturally right associative. Exactly. However, here they are mandatory. They indicate that the first parameter is a function that takes something and returns the same thing. Yeah, it is that. We take a stop here, right? Usually we say that... Yeah, it's right associative. It makes sense because... Oh, wait, no. Sorry. If we go over here and just... Well... If we do this... Whoops. Right. We take this and then we return this whole thing. Actually, let's add one more. Right. First we take this number and we return this whole thing. Well, this type, and return a function with all these things. But if we just want the function here to return a type and not a function, or whatever, we can order operation things here, right? That we don't. We take this and then we return this. And then on all of this, we return... Yeah, it's an order of operations thing again. We'll get in on tab says, ooh, they used naturally? Wait. Yeah, naturally. It is its nature. I mean, I suppose that word. Normally would be a better word, right? Right associative. However, here they are mandatory. They indicate that the first parameter is a function that takes something and returns that same thing. The second parameter is something of that type also, and the return value is also of the same type. Yeah. Oh, right. It says here that this here is not a function. This thing does not return a function. This thing returns a type. There we go. We could read this type declaration in the curried way, but to save ourselves a headache, we'll just say that this function takes two parameters and returns one thing. The first parameter is a function of type. Yeah, this is the first parameter. Oh, I like that. That's a good way of looking at it. The first parameter is a function. I like that. That's a way easier way of looking at it, indeed. Ugly rhetorics? No, we're not doing rhetorics here, Colgate on tap. This is not rhetorics. They're just explaining how this thing works. So it's not really a problem, I don't think. They're not trying to convince us that this thing is right associative. Right? There's a big difference between opinion language and just stating is and ought statements. This is an is statement, not an ought statement. So it's not an argument. There is no rhetorics in here. So no, it's not ugly rhetorics. And it actually, I think it's fine. It works fine here. The word and the way to use it, indeed. Because we understand. Maybe semantically it increases the uses of this word itself. Like you build a norm around using this word. Or not building, but perpetuating. That might not be the best idea. Right, the first parameter of the function is a function and the second is an a. Oh yeah, I like this. This is one parameter and this is the second parameter, and here we return it. Yeah, exactly. The function can also be int to int or string to string or whatever, but then the second parameter to also has to be of that type. Is that a... But then second parameter to also, yeah, that doesn't fit there, does it? Huh? Colgate InnoTab says it takes a function that takes parameter of type A and returns value of type A within parentheses as a parameter. Exactly. And returns a function that takes a parameter of type A and returns value of type A. Exactly. I really like that. That's how you read the parentheses. This is one parameter. If you just look at it that way, I think this is very readable. This is one parameter, because then this all makes sense, right? We have this, that's the first parameter, and this is the second parameter. Yeah, I really like that. Yeah, okay. No? Alright. Alright, note, from now on we'll say that functions take several parameters despite each function actually taking one parameter and returning... Wait. Actually taking one parameter and returning partially applied functions until we reach a function that returns a solid value. Yeah. For simplicity's sake, we'll say that A returns A takes two parameters, even though we know what's really going on under the hood. Yeah, that makes a lot of sense. I like that they explain this, and it might become relevant later on, but I'm assuming for most situations it's easier to just say, well, this is a function that takes two parameters. But I like how they described it, yeah. Colgate InnoTab says, pretty readable that way, but quite wordy when you try to put it into words. Oh, which one? This? It's readable, but wordy? Ah, suppose. Stuff always becomes that way, though. When you try to explain something, you can go on and on and on about describing things. You're not supposed to stand there. Nope. Not allowed. Suddenly, big cat. No, small cat. The body of the function is... Wait. The body of the function is pretty simple. We just add the parameter f as a function. Yeah. Applying x to it by separating them with a space and then applying the result to f again. Anyway, playing around with the function. Apply twice. Plus 310. 16, exactly. Apply twice, plus... Oh, plus hey. Yeah, exactly. We just apply it twice. Ooh, I like that one. This was actually a little bit helpful about the... I don't remember what they're called, but making an infix into a prefix by parentheses, right? Since... Oh, right. Actually, I was kind of saying that, right? That infix was... Well, maybe not a waste, but having infix function added to confusion. That you have multiple different syntaxes, right? I talked about that. That was over a week ago, I think. I don't know, but here we can see a way to do the... when we make something into a prefix, or when we call it as a prefix, we can see... Yeah, when it takes two... When we have a function that takes two parameters, and we do it with the parentheses, we can do it like this to decide what order things happen in. I like that. Alright, mult 3, 2, 2, 9, alright. Yeah, it's just we have a function that does functions multiple times. Right, the awesomeness and usefulness of partial application is evident. If our function requires us to pass it a function that takes only one parameter, we can just partially apply a function to the point where it takes only one parameter and then pass it.